Um, if there aren't any other questions, I guess we can get started. Okay, intro to triangles. So hopefully everyone here is like pretty familiar with a triangle, but could people maybe like throw at me some properties they can think about of triangles that they think like are pretty obvious or less so? Yeah, exactly. So there's three sides, three angles. Yeah, exactly. Yes, an internal angle sums to 180. Anything else? I think honestly that covers it pretty well. Yeah, it's a three-sided polygon and it has three edges, three vertices, interior angles. So that means like the angles on the inside. So if we're looking at our triangle, it'll just be like the sum of these three angles is 180, and the exterior angles add to 360. I think this is slightly less obvious, but it would basically just mean that the exterior angles, this one, and this one, add to 360. Yeah, so there are three angles, as in like there are three angles inside our triangle. Um, and there are also, okay, like, can people tell me what types of triangles they can think of? Yeah, so yes, there's yeah, equilateral, isosceles. There's also yeah, scalene and obtuse. So these are just like us obtuse angled and acute angled and right angled triangles, right? Yep. So this is mainly it for just what a triangle is. And then we're gonna go into a little bit of similar and congruent triangles. How many people here like know what similar and congruent mean? I think this is a bit more like complex. So like jumping from what a triangle is. Yeah, exactly. So congruent just means when two triangles look the exact same, they are the exact same shape, they're going to be referred to as congruent. For similar, it's more of like, these two triangles, they are the same shape, but not necessarily the same size. Then they would be considered similar. A more formal definition is what we'll be covering. So yeah, similar change by ratio, exactly. Yeah, so similar triangles are like two triangles are similar if they are the same shape, but not necessarily the same size. So that would mean that if we look at these two triangles, like just looking at it by eye, we can tell they look like fairly like the same shape, right? And if we wanted to prove that they were the same shape, we'd be looking at the angles. So we can see that this angle and this angle are equal, and they're called corresponding angles, right, of our different triangles, of our two triangles. And then these two angles are the same, and the third angle is also the same. Then that would mean they are the same shape, right? And then corresponding sides are proportional. So that just means that like this triangle, our first triangle and our second triangle, like our first triangle is just the second triangle, but made a little bit smaller, right? But the ratio between the sides remains consistent. So like if it's A, B, C, like the three sides of our first triangle have a ratio of like A, B, C, right? This doesn't change when we make it smaller and into triangle two. It could be like some factor times like I don't know, some factor K KB and then KC. But the ratio doesn't actually like change. So our three sides might become something like this. So the ratio, because the K's can just sort of cancel out, just remains still the same, right? Yeah. And there are several ways we can show that our two triangles are similar, and they're listed here. And AA stands for angle angle. So that just means if we are able to somehow prove that two like corresponding angles in our separate triangles are equal. Like so say let's say this one and this one, we've proven they're equal, and then we also managed to prove that this one and this one are also equal. That's enough to show that these two triangles are similar. Can somebody tell me like why we don't need to prove that the third angle is equal or like why it's not A, but just A. Yeah, like exactly. So the third angle is fixed, and what that means is we sort of go back to um one of the traits of a triangle, right? It's that the interior angles add to 180. Now that means that what would this, okay, say like this was angle like one and then angle two. What would this third angle be to?
180 minus 1 minus 2.
Yeah, exactly. It would be 180 minus angle one minus angle two, right? And then this other triangle we can also work out is also going to be, sorry, like I didn't mean the angle is one and two, like as in degrees, as in I label it one and two. So it's also 180 minus one and then minus angle two. Yeah, so we find out that okay, actually we don't need to really prove the third one is the same because it just kind of follows naturally, right? Yeah. So we usually just refer to it as like angle. And by corresponding angles, I sort of mean that like if you just look at the shape, in the two triangles, there are going to be a pair of angles that are like the same. So for the example, A and P over here, they're the same angle. So we can just say that they're corresponding angles in the similar triangles. Yeah, so I sort of refer to like as that. But yeah, okay, cool. And then another way we can do it is side angle side. Now, does anybody know what that means, sort of?
Like maybe if you get one angle and the two sides, then the you can put the other side on, and then you can know the other two angles.
Yeah, so for side angle side, I think it's one of the less obvious ones. Like, so for angle and side, it's pretty like intuitive what it means. Um, but for side angle side, what it basically means is that if we are able to prove that this side, say it's like length A and KA and KB. So for similar triangles, uh, if we're able to prove whenever there's an S, instead of thinking about a side, it's more of a side ratio, right? So if we're able to prove that A and I guess KA is equal to B and KB, which it is, so like they share a very common ratio, and we're also able to prove that the angle that is jammed between these two sides is equal, then we are able to prove that these two triangles are similar. But it's side angle side for a very specific reason. And the angle has to be the one that is jammed between our two sides, right? Like it has to follow the order of one side and then the angle and then the other side, right? So it has to sort of look like this shape in the two triangles. And if we're able to prove that the sides like have like a common ratio, so it's like I can find this consistent ratio between comparing the two sides, and I can also prove that the angle in between is the same, then that is sufficient to show that they are similar triangles. Does that make sense to everyone? Yes, no, maybe.
Yeah.
Yeah, okay. That's good to hear. So basically it's just that. Side, I think is also one of the easier ones to understand. It's basically just saying the ratio of all the three corresponding sides are like the same. So if this was C, then this would have to be KC for it to be for us to prove that these two triangles are similar. Because what is A over KA? Like if I could simplify it. Um, and in case I didn't make it clear, like A, B, C are all lengths. So like they're the length of our sides. Yeah, ratio. Like I guess if we were to simplify it, we could literally cross out A, right? And it'd just be like 1k. B over BK is the same. It's just like 1 over k as well. And then C over CK is still just 1 over k. So we notice that all of these, like through all the corresponding sides of our two triangles, they have this common ratio, which we can sort of find. Then that's also enough to show that these two share the same shape, right? Not the same, definitely not the same size, like unless k is equal to 1, but like we can know that's the same shape. Okay. If we put them all, if you put all of them divided and hmm. Could you explain that if you put all of them divided and they have the same ratio is the same. Oh yeah. Okay. That's a statement. Okay, cool. Yeah. So um yeah, they all have the same ratio for the corresponding sides. Okay. Is everyone happy for me to move on?
Wait, I'm copying it.
Okay, yeah. Don't feel pressured to like copy everything down because I will send out. You can find the video after class, and then you can also like get the notes after class as well. Yes. Okay. I guess I'll give you guys a little bit of time to digest if you need to. Um, okay. Okay, I will move on. Okay, next part is congruent triangles. Oh, and also just to mention, this notation comes up a lot. It's like a squiggle. And usually what people will do is like to show two triangles are similar, the notation is like ABC similar to PQR. And that just means these two triangles are similar. Yeah, it's just a notation thing. Okay, cool. For congruent triangles, I think it's actually like a little bit easier to understand than similar triangles. For congruent triangles, it basically just means that these two triangles, oh, congruent, that's a typo. Okay, the two triangles are congruent if they have the same shape and the same sides. So that not only means that the corresponding angles are equal, um, but the corresponding sides have to be exactly the same length. So this time it isn't just like a common ratio, it has to be like the exact same length. And this notation is like a squiggle and two lines, a squiggle above an equal sign. It just means A, B, C, and E, F, G are congruent triangles. Okay, I noticed someone has said confusing in the chat. Is that like, is there something I should clarify or you would want clarified? Feel free to let me know, like, because I obviously want everyone to follow along to the best they can. Oh, yeah. Okay, yeah. The squiggle thing is just common practice. I don't actually know why it has to be like a squiggle, but it's just how people write it because it is like quite wordy to be writing, oh, these two triangles are similar, and a lot easier just to do like one single squiggle, right? Okay. Okay, so now the ways to show congruency are very similar to the ones to show similarity. We could do it with side, side, side. So that just means that proving the like all three pairs of corresponding sides are the exact same length. So if you see these dashes on the lines, the same type of dashing means that these two lines are equal. So that would mean AC is equal to EG. So if we prove that AC is equal to EG, we also prove that AB is equal to EF. And then we also prove that BC is equal to FG, all in length. Then that's enough to show that they are same shape and same size. Side angle side, this time it's basically what we were talking about before in terms of the ordering. So we already talked about a side angle side, but for in this case, it would be we have to prove that these two lengths are the exact same, and then we prove that this angle over here is the exact same, and then we prove that these two lengths are the exact same length, right? So before the side was more a ratio, this time side is actually just like the length, so they have to be equal. And then another one is angle side angle. Um, Now, I guess, does anyone like think they might be able to explain this one or have any idea as to like why oh, it's two angles and a side? Why like you need to show why showing two angles are the same and then showing one pair of corresponding sides is the same as enough. What does showing two angles are equal? What does that mean? Yeah. Okay, so like we talked about before, if two angles with like two corresponding angles, we've managed to prove that they're like equal. For example, like this red one I've marked here and maybe this one down here, we've been able to prove that these like corresponding angles are equal, then it follows very naturally from what we talked about before that this third angle has to be equal as well, right? That's just like the property of triangles. Now, that's why there's two A's, right? So after we have figured out two angles are the same, we basically know these two shapes are similar, right? But congruent is a stronger condition than similar because it's the same sides as well. So now, if we're able to prove that one of these lengths are the exact same um, length, then that means, okay, our triangles are actually congruent. So they're not only similar, but they're also congruent. Does that make sense to everyone? Um, mm, we you could do like a lot of trig on triangles, but I guess that's just not what we're going to be talking about today. We're just going to try avoid trig altogether. Yeah, so don't worry about that. I think it's like a lot easier. Um, you don't have to use trig. Yeah. Okay, is everyone following along? I will move on if everything is all right. Okay, I'm gonna take that as everyone's following. Okay, cool. So now Pythagoras. How many people have heard of the Pythagoras theorem? You could like raise your hand or just like type in the chat. Okay, perfect. Yeah, I think Pythagoras theorem is something you come across fairly early on. So I'd expect some of us to know. Yeah, exactly. So Pythagoras theorem is mainly it's just to do with right angle triangles, right? So for a right angle triangle, which is a triangle with like a 90-degree angle, we know an interesting fact about the relationship between the lengths of the triangle, and that's a squared plus b squared equals c squared, right? And so that just means this is the right angle. So this is the 90 degrees. And then the hypotenuse has to always be like the C we're referring to in our equation. And then we label the other two sides like A and B, however we want. Like it doesn't really matter because they mean the same thing in the equation. It just means that the length of A squared plus the length of B squared is going to be the length of the hypotenuse squared, which is just C squared. So this is just a condition we know about lengths of our right angle triangle. Does that make sense to everyone? Yes, exactly. So the hypotenuse like is the longest side of the right angle triangle. You can also think about it as the side that is opposite the 90 degrees. So like if this is our 90 degrees, the side that our 90 degrees doesn't touch is going to be our hypotenuse. Yeah. So okay. Uh that's honestly all I had to talk about for Pythagoras. But let's do a quick exercise and let's say I have a triangle that's like it's not a good diagram, but this I know two sides and I want to work out the third. How would I do that? Yeah, okay. Exactly, right. So we can actually just use the Pythagoras theorem to work out our third length. So we don't know the length of, in this case, the hypotenuse, which is C, right? So we know we could, if we wanted to, we can label this A, we can label this B, and that would mean 3 squared plus 4 squared is going to be, this one's going to be c, so this one's going to be c squared, right? So 3 squared is 9, 4 squared is 16 equals c squared, which is that's c squared equals 25. And if we take the square root of both sides, that's just going to be c equals 5. Yeah. So I think Pythagoras is most useful when you know two sides, the length of two sides of your right angle triangle, and you're trying to find the third. So that's always helpful. Okay, and then third section, we're just going to be talking about triangle centers. I think triangle centers is like a bit of an is a bit harder than what we've discussed. But we're just going to be talking about some like them generally, so we won't be going into too much detail, but we'll see how that goes. Okay, and if anyone has any questions, just shout out and let me know. So, like if you're thinking about a center of an object, like usually like it's very obvious for symmetrical objects, like I don't know, like a square, you could pretty like it's pretty obvious like where the center is, it's just the intersection of our diagonals. For a circle, it's also pretty obvious where the center is. For a triangle, there are a lot of different types of centers, and they're all useful or like they're all interesting in their different way. Yeah, so and they all have different definitions. It's not really just what you would think about, I think, as a center, but okay. I think it makes more sense after we go into it. So the first type of center we're going to talk about is the orthocenter. So the orthocenter, or in our diagram, the point that we've labeled with H, is where the three heights of the triangle cross, right? And heights is sort of a less technical term, but it just basically means where the altitudes of the triangle cross. So I'm sure everyone's familiar with when you're referring to height in a triangle, it's usually just like you take a line from one of the vertices and you like that is perpendicular to your base. So if you're like trying to work out area or something, you'll always like draw out your height of your triangle, or you often can do that. So this is why I'm talking about when I'm saying height. And now the triangle has 3 heights, right? Because it has 3 vertices. So I could draw also a line that's perpendicular to the other side, and I can do the same for this one. So an interesting fact is that actually after I draw all 3 of these heights or these altitudes, they actually cross over at the exact same point. So if I draw on 2, there's an intersection here, right? What's interesting is that if I actually draw out my third one and it's perpendicular or like at 90 degrees with my third side, it actually crosses over this point. So it doesn't do something funny like this and then create 3 points. It actually crosses over the intersection of my other 2 altitudes. So this is why it's like a center, because it's a distinct point. So I think that's just an interesting fact that they all cross over at one point. And yeah, so altitude is a straight line from the corner of the triangle down to the opposite side, forming a right angle, as you can see in the diagram. And yeah, all 3 heights of the triangle meet at one point. And if for anyone who's like maybe out for a challenge, maybe try proving this fact. I think would be really interesting. Like proving that these all 3 lines actually intersect at one point, which is the orthocenter. If anyone's up for that, I think it goes into like some other content we haven't really talked about in today's lesson, but if you feel you're up for the challenge, go ahead. Okay, the next type of center I'll talk about is the circumcenter. So it's where the 3 perpendicular bisectors of our triangle sides meet. Now, perpendicular bisector, is there an explanation why they cross? Yeah, for sure. Like, I think there's definitely like a proof, and I don't think it's that bad. But it does cover more, like at least the proof I know covers more material than we have covered today. So I won't go into the explanation, but for anyone who's interested or like wants to prove it themselves, go ahead. Or we're probably going to talk about it later in the program after we've covered like the material we need to actually be able to explain it. Yeah, so yes. Okay, cool. So now circumcenter, like I said, what it was, and then the perpendicular bisector is basically a line that cuts another like exactly in half at a right angle, right? So if we're talking about like a perpendicular bisector of a line, say like A, B, it means that okay, this would be considered a perpendicular bisector. So the first condition is that it is at right angles with our line. But the second condition is that it actually cuts our line perfectly in half. So that means this length here would be equal to this length here. So that's what the perpendicular bisector is. So basically what the circumcenter is that like, again, we have three sides in our triangle, so we're gonna have three perpendicular bisectors for each of the sides, right? I could draw them on here. Basically means this is a perpendicular bisector of AB. This is going to be the perpendicular bisector of AC, not a good one, but sorry. And this is going to be a perpendicular bisector of BC, right? And again, funnily enough, these three lines also are concurrent, or like they meet at the same point, right? And this point, which is labeled O, is referred to the circumcenter, right? And the circumcenter is also the center of a triangle circumcircle. So does anybody know what the circumcircle is? Like previous to what's been like this class or anything? No, that's okay. Like basically the circumcircle is just a triangle that passes through all like three corners of the triangle. And the circumcenter of our triangle is going to be the center of the circle that does pass through all three corners of our triangle. So like for any triangle, you can sort of find a circle that's going to pass perfectly through the three vertices, and then the center of this circle is going to be our circumcenter, which is going to be the point where our angle bisectors meet. Yeah, okay. And again, I think a proof would make a lot of sense after we do a tiny bit more material. But one thing I will mention is that like I think perpendicular bisectors come up a lot when we're dealing with isosceles triangles. So I think a lot of us know what an isosceles triangle is, right? So it's basically just a triangle which has two equal sides, right? And what happens is that we can actually draw, if we draw the height from like this side that is like this vertex that is like adjacent to our two equal sides, and we draw the height, this line actually bisects this line, which means it cuts in half. So this side would be equal to this side. And I think or else we could also say that if we drew the perpendicular bisector of a line, and then we constructed a triangle with it, like it could go all the way up, and we constructed a triangle with it, no matter if I did it this point or this point, or like whatever point on this line, as long as it perpendicular bisects like the base length, all of these triangles are going to be isosceles. So all of these triangles, like you can see probably three of them, they are all isosceles triangles. So that means this length is equal to this length, and then this length is equal to this length, and this length and is equal to this length. Can anybody think of why? How do you find an accurate perpendicular bisector? Oh, okay. I think like the definition of a perpendicular bisector is always the same, right? Like it just first you have like a line and then it cuts it in half, but it's also perpendicular or at 90 degrees with our line. So that is the definition of a perpendicular bisector. if your question's like how you can draw an accurate perpendicular bisector, like um I'm sure there are like ways to do that. But like in a problem, I don't think it would ever be uh like it won't be a problem to find an accurate perpendicular bisector. Yeah, so okay, so a really good idea from one person is just like the triangle is like there's some sort of symmetry going on, right? Like, or else we could talk about it in terms of congruent triangles, right? I will just take one of these triangles, for example. Okay, say I took this triangle, right? At this point, I don't know these two lengths are equal, and I want to prove it, right? I want to prove that this triangle I have here is going to be isosceles, and all I know is that I'll label points A, B, C, D. I know that AD is perpendicular bisector of BC, right? This is the fact I know, and I want to prove that AB is equal to AC, or my triangle ABC is isosceles, right? So can anyone see a congruent triangle going on here? Congruent triangle going on here, or two? Yeah, so Kinsley, I noticed Kinsley raised his hand. Do you want to? Yeah, so more people are noticing it. Yeah, exactly. Does anyone know like how to come up with a proof for this?
And a
Just
triangle
from, yeah,
inside outside of the actual triangle.
sorry?
The triangle circumcenter be outside of the triangle.
The circumcenter can be outside the triangle. In this case, it would actually, yeah, it would definitely be outside the triangle. Yeah. It happens like when your angle is like, notice how this angle is really big, quite big. So if we actually envisioned our circumcenter, it would be like somewhere here, right? And that's outside the triangle. And that's totally fine. So it's I guess it's not how you traditionally think of a center, but yes, it can definitely be outside the triangle. Yeah, so I'm seeing a lot of really good ideas, right? So, and I think a lot of these will work. If we were to think about it as some congruent triangles, we notice that we can do side angle side on this. So we obviously know that BD equals DC, right? That's the condition we're given since that AD is perpendicular bisector of BC. So these two lengths are equal. We already know that. The angle we know are equal is we know that ADC is 90 degrees, but what is ADB? What is the angle ADB? Yeah, do you wanna, the person who raised her hand, do you wanna say?
Is it also 90 degrees because the
Yeah,
line is like 180?
yeah,
And
yeah. So they,
also, can you also prove like the triangle is congruent because like using SSS because you could use the Pythagoras theorem to
yeah,
figure out AB and AC?
yeah, exactly. Yeah. So, like people mentioned, you can use Pythagoras straight away, right? Because BD is equal to BC, but they also share the line AD. So clearly AB is going to be equal to AC. I was going to do it through side angle side. So we know that these two lengths are equal. We also know that these two angles are equal, and they share the side here, right? So this is the case that we were talking about before of congruent triangles, side angle side. So the second one. So we actually apply it to these two like triangles inside our larger triangle, and we're able to prove that they're congruent triangles, right? And now the condition for congruent triangles is that the corresponding sides are equal. So that would mean that AB is just equal to AC, right? So that's another way we can prove that um, it's an isosceles triangle, right? Okay, with the perpendicular bisector in place. Are the two triangles formed independent? Yeah, for sure. So the interior angle sum of any triangle you can form that is like close, like obviously you just got three vertices, three sides. On the interior sum is 180 degrees. even if it's been like a larger triangle cut up. Yeah, anything. Yeah, exactly. So like orientation doesn't really matter. They're still congruent, even if they like face different directions or like have been rotated strangely. Yeah, okay. And I guess the reason I brought this up is because perpendicular bisector obviously comes up, so it's an interesting fact about perpendicular bisectors, but it also shows that because we talked about like the circumcenter is constructed by the intersection of the perpendicular bisectors, this would mean that this line here are equal, right? Because AOB is going to be an isosceles triangle by what we proved previously just then. So these two lengths we know are equal. But if we're looking at the triangle COB, it's also isosceles, right? So this side would also be equal to the green sides, right? So that just means that all these three sides are equal. And obviously we know that the radius of a circle is constant. So I guess that's also like one way of seeing why O would be the center of the circumcircle. Yeah, so all of these green lengths would be the radius of our circumcircle. Okay, cool. I think that was just sort of a side note. Okay, I think we can move on. Okay. Now for the centroid as another center. The centroid is the point where the three medians of a triangle intersect. And a median is a line which joins like the one vertex to the opposite side of the triangle and then cuts it in half, right? So we talked about perpendicular bisector. That's somehow also cuts lines in half. But for this one, it's basically you take one of the vertices and you draw a line to the opposite side, and then it cuts the opposite side in half, right? So that's how it's defined. And basically, the three of them from each vertex just intersect at the same point. And this point is going to be known as the centroid. Yeah, okay. Does anyone have any questions about like what a median is or anything? Or like how a centroid is defined? Yeah, so like orthocenter, remember it's like 90 degrees, right? So for this one, it comes down and all I know is that it cuts my line in half, right? It cuts the side in half. But if I were to draw the orthocenter on this exact same triangle, I would go from like a vertex as well, but in this time I'll be drawing a line that is perpendicular or at 90 degrees with my baseline. So do you see why these 2 points are like different, or how an altitude is different to a median? So if I were to draw the same thing for my other vertices, like my orthocenter would be somewhere here. So you can see very clearly for this triangle that they're actually two separate distinct points. Yeah, and the definition is just different because this one talks about medians, the other one talks about altitude. Where altitudes are to do with like 90 degrees or like heights, right? And medians are more to do with like cutting lines in half. And perpendicular bisectors are like a combination of both, but you don't go from the vertices anymore. Okay, so I think this last one. Okay, incenter. So the incenter is the point at which the bisector of the interior angles meet. So now the bisector of the interior angle is a line that cuts each of our interior angles in half. Right, so bisector or bisect in general means like to cut things in half. Right, so in this case, the bisector we're talking about is going to be like this line, and this line. And what these lines do is like basically I start from one vertex. They cut the angles, like they cut my interior angles in half at each of the vertices. So you can see that like this angle would be equal to this angle, this angle, this angle, this angle, this angle. So it's basically like cutting all my angles in half, and then these three lines also meet at the same point. Okay. Does that make sense to everyone? And also, for a triangle, there is also an incircle. So that this is like while the circumcircle is this circle that goes on the outside of our triangle and passes through the three vertices, there's also like a circle that can go on the inside of our triangle that sort of sits very nicely inside our triangle. Like that's a terrible circle, but like there's going to be a circle that can just sit nicely inside my triangle, and that's called the incircle. So the incenter is going to be the center of this incircle. Okay, and yeah, okay, so how do we know there are always these two circles? I guess again, we'll probably cover these proofs or at least like an explanation in more detail later. Yeah, but it's a very good question. Yeah, cool. Okay, does the definitions of these centers make sense to everyone? So if I know there's going to be like a lot of questions like about these sort of centers, and there's a lot of properties to do with these centers, but we don't quite have enough time to like, and we don't quite have enough I guess, knowledge that we've covered so far to explain all of it. But does the definitions make sense to everyone? Yes, no, like give me a thumbs up or like shout out if you have any questions related to the definitions. Okay, some people have reacted, not everyone. Let me know if I think I get okay. Let me know like which parts you think. Okay, yeah, for sure. It definitely can be a little bit overwhelming, but is there any specific parts you think like would help like your understanding of? I can't imagine as a schoolie. Okay. I guess so far, I think all I'd expect you guys to sort of have, oh, okay. Yeah, no, like clearly, like it's very valid not to see why these centers are important or like why I need to mention them. But after you start doing some geometry problems that have like a lot of more content and stuff, these centers become like they either get mentioned in the problem statement quite a bit or like they help you solve problems. And that's because you know certain properties about these centers that can like help aid you in completing and solving a problem. Without sort of more context of this, they can seem like not important at all. But I guess it's good right now just to know like sort of what these centers are, and we'll cover in more detail, like when we come across it, how these centers exist, and like some other properties to do with them. I think right now, just know that like orthocenter is the intersection of the altitudes. Circumcenter is the intersection of the three perpendicular bisectors. Centroid is the intersection of the three medians, and incenter is the intersection of the bisectors, angle bisectors. So if you could remember these definitions and know that such a point exists, I think is just sort of what we're trying to cover today. We have around 10 minutes, so I was actually hoping we could do a Kahoot just to sort of cover some of the content we've talked about today. Okay, does that sound okay to everyone? Okay, cool. I will get that started. Yeah, and if anyone has any like more specific questions that they want to ask, you can do that like you can email us or you can like after class or anything. Obviously, I also know there's like a range of abilities or like prior experience here. So like if you think you want more extension or you want like some more explanations, you can just let me know and I'll try answer any questions you guys have. Okay. Yeah, I'll give a maybe one more minute and then we can just get started. Is anyone like waiting to come on who hasn't been able to go? Because everyone's still trying to get on. Okay. You can type in the chat if that is the case, and then I can wait a little longer. Okay. Is everyone on? Hopefully. I'll get started if everyone is. Okay. I think it's a good time to get started. Okay, cool. Most of these questions are not hot, so like just speed run them. Ooh, nice. Yeah, for this one, it's like uh a little bit it's actually a little bit tricky because ASS is like the ordering while SAS works. ASS doesn't work because the order is not right. If the angle isn't between the two sides, then you can't really prove that it's similar that way. Angle definitely does work because like we talked about before, if two angles are equal, the third angle is like automatically equal. So they share the same shape. Okay. Nice. Yeah, this one's this one I think it's just yeah. Nice. Cool. Yeah, so it is the orthocenter. Cool. Yes, it is the circumcenter that passes around the three vertices of our triangle. Ooh, yeah, so congruent triangles mean that they're same shape and also same size. So that means the sides have to be equal and the angles are also equal. Nice. Yeah, so centroid is just the intersection point of the medians. Um, the centers are really hard to get your head around when you're first introduced to them. When you learn more properties about them, and then when they come again, it becomes very natural. But yeah, this is sort of just a memorization thing, so like, don't worry if you got it wrong. Nice. Nice. Okay. Yes, so that is well, I think the name sort of gives it away pretty well, like in center and circle. Uh, but yeah, it is the center, the in circle. Oh, I don't know if we talked about the triangle. I will talk about it in we mentioned it, but it was not, yeah, covered in detail. Yes, yes. Wait. Okay. Violates. Okay, sorry. I didn't even read the question. Yeah, yeah. So, the triangle inequality basically means like you obviously have three sides of your triangle. If you take the sum of the lengths of any two sides in your triangle, it always has to be strictly larger than the length of your other side. And that's like true for any triangle. So the other three are not correct. Like the yellow one is just not correct because I don't think it has much to do with the triangle inequality. Like I'm not sure actually what's going on there. Um, but oh, I think I wrote the actual answer wrong as well. But like the two sides. Okay, I see why so many people chose yellow. And I was supposed to say B plus C greater than A. I think I accidentally typed it twice, so that's why it looks sort of funny. But it basically means that all if you look at any of the other options, any two side length is greater than third, which is good. For green, the two side lengths is smaller than the third, which is bad, and that violates the triangle inequality theorem. Yep. Okay. This is some quick math. Nice. Yeah. So basically, how it should be done is like a squared plus b squared equals c squared. If we know the hypotenuse is 13, then we automatically know the value of c, which is our hypotenuse, 13. 13 squared, like if we rearrange our equation from a squared plus b squared equals c squared, it can be a squared equals c squared minus b squared, right? So we know one leg is 5, so let's say that's like b. And then we also know the hypotenuse c is 13. So it's just 13 squared minus 5 squared equals a squared. So the other leg squared. And 13 squared minus 5 squared is 144. 144 square root is 12. So that just means our other leg is going to be 12. We're almost done. Nice. Okay. Yeah, so this question is mostly to do with just the triangle inequality. So we know that two lengths of our triangle added together has to be strictly greater than the third, right? So for a 6, 7, 12 triangle, the two shortest lengths, 6 plus 7 is 13, which is greater than 12. So that satisfies our triangle inequality. If we tried with any other of the two pairs, we'll always notice it's greater than the third, which is good. For the other questions, if we look at them, so 3 plus 4 is less than 8. So that violates our triangle inequality because the sum of the two lengths isn't greater than the third because 3 plus 4 is less than 8. Same thing with 2, 3, 6, 2 plus 3, 5, less than 6. 5, 5, 10 is might be a little bit less obvious because 5 plus 5 is equal to 10. But if we think about the triangle inequality, the condition is like the greater condition is strict. So that means the sum of the two sides has to be strictly greater than the third. It cannot be equal. So 5 plus 5 is not strictly greater than 10. So that's why that one violates it. Okay, last problem. Oh wait, I think this one's kind of cool. But yeah. Okay. Yeah, this one was cruel. Um, Maybe because we didn't talk about
I
area
remember
ratio.
you have to square the ratio.
Yes, exactly. Um, I can see why a lot of people chose red because you might expect like, oh, if the side ratio, corresponding ratio is like 2 to 3, then surely the area is like 2 to 3 as well, right? But that's actually not really true. Actually, it would be 2 squared to 3 squared. So it'd actually be a 4 to 9 ratio for triangle area. We'll cover this, but I'll cover this next week in a bit more detail. But you can sort of think about it as like base times height. If the ratio of the base and the height are both 2 to 3, but you need a times base and height together to find the ratio, right? So you're timesing two things that are like ratio 2 to 3. That's 2 times 2 against 3 times 3. So it's like 4 to 9. Um, so the larger area would actually be like 4 to 9. So 16 is the 4, and then the 9 would be 36. Um, but don't worry, if that doesn't make too much sense, I'll cover it in class. Okay, let's look at the podium.